Hello, everyone. Thanks for joining us today. We're going to get started now. Thanks for joining us again. We are doing our webinar today. It's covering TigerGraph's graph query language called GSQL, and it's going to be the first webinar in a series. My name is Emily McAuliffe, and I am just helping moderate today. We have a few housekeeping items before we get started. Since all attendees are muted, you can ask questions via chat, and we'll have the Q&A at the end. You can also send your questions that we will answer at the end of the webinar via the Q&A tab in the Zoom menu. And we are also recording the webinar if you can't stay for the entire presentation. And after the webinar, we will send you a link to the slides and some other materials, including the recording. So with that, I'm going to introduce Victor Lee, who is our moderator today and our director of product management. And he has a PhD in computer science from Kent State University with a focus on graph data mining. And he has a long history in the tech industry. So I think I'll pass it over to Victor to introduce our other speakers now.
Thank you very much, Emily. So in previous days, I've had the pleasure of being the presenter for you, but today I get to do something different. I get to welcome two of my colleagues to present, and they have really been instrumental in the development of GSQL, the powerful and easy to learn graph query language that we've developed here at TigerGraph. So the first speaker is Dr. Eileen Deutsch. He is a renowned database researcher and professor at the University of California, San Diego. Dr. Deutsch has specialized in graph query language design and optimization for a variety of different data models, ranging from text to relational and post-relational models, with particular emphasis on semi-structured data. Earlier this month, he was awarded the Alberto O. Mendelsohn Test of Time Award at SIGMOD 2018. And also, he has been a consultant to TigerGraph for several years and recently accepted the position of chief scientist at TigerGraph. So we're really honored to have him with us today. Our second speaker today is Dr. Ming Shi Woo. He is our vice president of engineering at TigerGraph and was one of our founding software developers. He has led the initial architecture and development of GSQL. He's also contributed, of course, to many other aspects of the TigerGraph platform. So he's been with the company practically from the start. He knows all about GSQL and the platform in general. So we're going to start today with Eileen giving us some insight into the need for GSQL and its advantages. And then Ming Shi will take you through a tutorial showing you how easy it is to make your own graph and to write queries. That's all we'll be able to cover today, but in future video sessions, we'll continue to show you what GSQL can do for you to solve a host of real-world use cases. And then we'll conclude with some question and answer period. So, Eileen, turning to you. As we noted, you've been researching many different database models throughout your career, not just graphs. You've seen the development of graphs and why they've become more important recently. And you're also very well versed in all the different query languages, including all the existing major graph query languages. So we'd like to ask you, what are your general observations about these graph query languages and the applications they serve? And then if you could then move on to when TigerGraph came to you, you had the opportunity to help develop a better graph query language. What were some of your objectives and what are some of those features you proposed? Eileen?
Thank you, Victor, for the introduction. Thanks, everybody, for coming. Indeed, I've had the opportunity to watch the evolution of graph query languages over more than 2 decades now, and the current query language landscape is extremely rich, rather than me giving you a laundry list of systems and languages, let me tell you that they fall into a few programming styles that are adopted by today's data scientists when they write graph analytic tasks. Programming styles that are so distinct from each other that depending on which style you adopt today, you typically end up in a disjoint subcommunity from all the others. And one of them is the pattern matching programming style, in which the data scientist will write a little graph pattern that contains a bunch of variables, and the system will try to match this pattern against the underlying data graph in all possible ways, in the process binding the variables with values found in the graph, which then the programming languages allow you to further post-process. This is a highly declarative style in which you don't tell the system anything about how this matching should happen. In a very opposite extreme, you will find procedural programming style in which the programmer will specify how the graph is to be traversed step by step in order to reach the interesting values and then post-process them. So just to give you some examples, in the pattern matching camp, we have, starting from the Struckel query language from 20 years ago, a line that leads to modern systems such as Cypher from Neo4j. Whereas in the traversal matching and procedural programming camp, we have languages such as Gremlin. In addition, you will find data scientists who use no declarative language, but rather adopt a NoSQL style where they will write scripts in general purpose programming languages, often in order to specify tasks that are to be executed in parallel over the underlying data graph. And while these three communities think very differently and therefore have to subscribe to very different programming paradigms and systems, they don't contain the community of seasoned SQL programmers who have a need to go into post-relational data models because none of the languages of these categories look like SQL. So one of the objectives we were after when we started was simply to provide a language that would unify these disjointed communities by allowing any one of these data scientists to look at the same GSQL query and, depending on the hat they're wearing, to interpret it according to their preference. And we have come up with a language that we feel has a natural interpretation as a pattern matching language, if that's how you like it, or equivalently, its semantics can be given in terms of traversal of the graph procedurally, or equivalently, it can be given in terms of performing a bunch of MapReduce style primitives over the graph in its totality. And finally, the language reduces the slope of the learning curve for SQL programmers because it is pretty much inspired by SQL syntax. As Ming Shi is going to show you, this language allows you, among others, as you traverse the graph, to aggregate data that you find on the way in various flexible ways.
Okay, thank you very much, Eileen. So we're going to turn now to Ming Shi Woo, where he is going to give you a detailed look at GSQL. Well, just an introductory lesson. Maybe if you could start sharing your screen again, Ming Shi. And we're going to let you go through our so-called GSQL 101. Ming Shi, could you share your screen again, please?
Yeah. Can you see my screen now?
Yeah.
Okay. Yeah, thanks, Victor. I'm going to give a crash course on GSQL today. And assume that everyone have registered on our website and got the welcome email. And here I open a copy of that email. And in this email, it includes a lot of useful resources, such as the minimum hardware and software requirements, the download link of the TigerGraph dev and dev edition, and the GSQL 101 tutorial link. So I'm going to cover this link today. So to start off, you need a Linux box with a minimum 8 gig memory and 20 gig disk space. We support majority of the popular Linux operating systems, such as Red Hat, CentOS, Ubuntu, and Debian. You can follow the instruction in that email that I just showed you to set up TigerGraph fairly easily. And once you have successfully installed the TigerGraph, the first baby step I would recommend to try is to follow GSQL 101 within 60 minutes. So we have tested in many developers, and the average feedback is 60 minutes. For this webinar, I have set up TigerGraph Enterprise Edition on an EC2 machine. And this machine has 60 gig memory and 32 vCPUs. To save time, I've set up everything by following the GSQL 101 step by step. Now I'm focusing on explaining the DDL, the loading language, and the GSQL queries. I'm putting two terminals side by side. And on the left-hand side is a live GSQL terminal that I'm going to do some live demo. And on the right-hand side, I open a read-only text terminal. And so I can show what query and the DDL and what loading language I'm talking about. So I'm going to start now. So the first thing you need to do graph database is to create a graph schema. And user can define some vertex type and some edge types. They are very similar to the table or relation concept in the relational database world. A vertex type must have a primary ID field here. So I highlight what I'm talking about now. And this primary ID is used to uniquely identify a vertex instance. It's just like the primary ID in a relational table. And we use the primary ID to indicate this special field. So in this particular example, I use name, a person's name as the primary ID, and it has the string type. And a vertex type can also have 0 or more attributes. This is also a familiar concept in the relational database world. A table can contain multiple attributes and or you call it the columns. And then you can use this syntax, create the vertex and name, and then primary ID and column and name and column type to define a vertex type. Similarly, you can define an edge type. And an edge type must have two special fields. One is called from field, and the other is to fields. So intuitively, this from and to fields can uniquely identify an edge instance. And also you can have 0 or more attributes in this edge type. And what's special about edge is in the real world, you can model an edge as symmetric or asymmetric. So a symmetric edge type, you can think it as a mutual relationship between two objects. And there's no emphasis on one side. They are mutual. And we use the keyword undirected to indicate the edge type is symmetric. On the other hand, sometimes you really have asymmetric edge type. And in that scenario, we use a directly keyword here to indicate it's a one direction. And if I use a directly keyword to define edge type, then the edge can only go from the vertex type and to the target edge type. So it encodes the direction of the edge type. Here, we also can allow 0, 1, or more attributes for the edge type. So in this particular social graph example, I use connect date to indicate when the two persons become friends. And the attribute type is daytime. So after we define a set of vertex type and a set of edge types, I can define the graph. To define a graph is the simplest DDL in this DDL command set. So just create a graph and give a graph name. And then you put a list of the vertex type and the edge type into this graph. And that's define a graph. Here in our running example, I define a social graph. And the social graph consists of person vertex type and the undirected friendship edge type. And the friendship edge type connects two person vertex type, and they're symmetric. And after we define the vertex and edge types, now we want to load data into it. And in order to load data, it's essentially a mapping problem. We need to define a set of mapping from source files and to the central graph schema we just defined. Our GSQL language has a powerful loading language to assist the user to accomplish this goal. And there are two steps in order to load data into TigerGraph. The first step is to define a loading job. And this job needs a name, and also it needs a target graph. So I give the name of the loading job load social, and I target the graph social. And there are basically two components or statements in this loading job syntax. So I first need to define a set of file name variables. Each file name variables essentially represents a source data schema. We can change the source file at runtime as far as the schema is not changed. And here I define a file name variable, file1, and it's associated with the schema that in person.csv. And also I define a file name variable, file2, and it associates the schema with friendship.csv. And person.csv has, I can quickly show it. Okay. Okay, let me see whether I'm on that folder. Yeah, person.csv has name, gender, age, state, 4 columns, and I have 7 rows to represent 7 people. And friendship.csv has 3 columns. And the first column is person 1, the second column person 2, and the third column is the date they become friends. Now the second part of the loading script is a set of loading statement. So line 20 and 23 are 2 loading statements. And the syntax for the loading statement is we load the file name variable to a target vertex or edge type. And you just say load the file name variable to either vertex or edge, and the vertex or edge type name. And the values clause define the mappings. So the value clause contains the target, has the same length as the target object schema. And then it specifies the source file column reference. So there are 2 ways to reference the source file schema. And the first one is referenced by name. So you can use the column name from the source file 1. The second one is referenced by position. So you can use 0 represents the first column, and $1 represents the second column. So in this particular example, I illustrate both reference type. So in the first loading statements, I say map file1 column name and to the primary ID field of the person vertex type, and map file1's column name name to the name attributes of the person vertex type, and map the file1's column age to the age column in the person type, and so on. And here I use the using clause to specify the heterogeneity configuration for the file1. So I say header equals to true. It means the first line of file1 is metadata, and it contains the header line, and we should not load that line. So basically, let the loader skip this first line. And separator equals to comma. It means it's a CSV file, and when we tokenize the file line by line, we look at this comma as the delimiter. And similarly, for file2, I also say header equals to true. So I tell the loader to skip the first line, and I tell the loader to use the comma as the tokenizer delimiter. And I map column 0 to the from clause, column 1 to the to field, and column 2 to the connect by attributes. And this can be going from 2 loading statements to hundreds loading statements. So it's essentially integration loading language, and it's very powerful. After you define this loading language, you can run the loading job, and you just use the syntax run loading job and loading job name, and then it will kick off the loading. So before this seminar, I have preload the data into our graph. Now I'm trying to use the graph. So the graph name is social. So I'm under social. So I run some built-in query to do some object inspection. The first one I'm going to try is to see how many objects in the person vertex type. So the syntax is very familiar to the SQL users. So in the from clause, you can use the vertex type as the place where you put table. And then it returns JSON objects. So in our graph database, we always return JSON objects so that it can have easier integration with application. So this person vertex type contains 7 objects. And now I can do edge inspection. So I run this. So I select count from edge pattern. So this edge pattern is a friendship and start from person vertex type to another person vertex type. And the return result is 14 edges, and they are all having the friendship edge type. I can also do some filtering. So for example, I want to find the vertex instance whose primary ID is Tom, and then this returns vertex objects. And it has the vertex ID, Tom, and the attributes objects. I can also do other attributes filtering. So for example, now I want to find all the person's name who live in the state, California. And then I do this filter in the where clause, and I return 2 objects and their name attributes. So Emily, Tom, and the name. And I can also do some other filtering. So let's try one more. So this time I find all the people who are whose name and their age, and they must satisfy the filter. Their age is above 30. And Tom and Dan from our graph database satisfy this filtering. And I can also do the filtering on edge filter. So this example, I find all the edges and that starting from Tom vertex, and this return 2 edge objects. The first one is edge starting from Tom and ending at the person Dan, and they become friends 2017 June 3rd. And the second edge instance is also start from Tom and ending to the person Jenny, and they become friends January 1st, 2015. Okay, this is a simple select point inspection language. But what makes GSQL is distinct from what is available on the market is really the parameterized GSQL query language syntax. And this is our focus today. I will start with very baby step and start with like a hello world in GSQL. So the first query I'm going to talk about is named hello. And its function is returning the one-hop neighbors of a given person. So the syntax is very simple. You just do it like PL/SQL in Oracle or SQL procedure in Microsoft SQL Server. So you can say create a query, and then you name the query, and then you have the parameters, person. And there are many types in the parameters, and one of the basic type is a vertex type, and then a parameter name, and then you specify which graph this query is designed for. And then this query body is a sequence of query blocks, and we use a single SQL blocks to traverse the graph, and each SQL block will generate a vertex set. We give name for each vertex set. For example, there are two query blocks in this hello query. A seeding block, start equals to P. A seeding block is basically assign parameter to some other set to the vertex set variable. And then there's a one hop edge block. And the one hop edge block will generate a vertex set named result. And like I said, the seeding blocks just assign the input parameter to the start vertex set name. And the one hop edge block is borrowing the select from where construct from the relational SQL syntax. However, the from clause in the GSQL is not a table. It is an edge pattern. The edge pattern is a triplet. It always starts from a vertex set. And the middle part is one or multiple edge type and constrain the edge pattern. And the rightmost part is one or more vertex type, constrain the target vertex types. Then this triplet essentially specify an edge pattern that we want to find those instances that matching this pattern in the graph database. For all the three parts of an edge pattern, we can add an alias by a colon and an alias name. And if you're not familiar with the alias concept, you can think of it as a variable name bind to the corresponding part of the triplet. So here I bind the source to the start vertex set. I bind the alias name E to the middle part of the edge type, and I bind the target alias to the target vertex set. And the benefits of introducing alias is I can use this alias anywhere in the select query block, such as the where clause or the accum clause and the order by or limit. And all these expression places, I can use the alias as a shorthand to refer to the corresponding part in the triplet pattern. Finally, the edge block can select either the source or the target vertex set. Because as I said, each building block in this query body is a vertex set. And the right-hand side of an equal sign will produce a vertex set and assign to the vertex set name on the left-hand side. The last statement is the print statement. So you can print a vertex set or a list of expressions. In summary, you can see this single hello query will return the one-hop neighbors of a given input person P. And after we write this simple query, we will call the install query and the query name to install this query to generate machine code. And then at the same time, it will generate REST endpoints. So you can treat it as a service, treat this query as a service, and supply different parameters to invoke this service. So let's try some queries. So I will first see who are the how many one-hop neighbors does Tom have. So I invoke this query in the GCQ shell. Okay, so it returns some JSON results. So the first few lines is the metadata. So the query is not in error, and there's no comments for this query. And the version of the social schema is version 1, and API of this JSON is version 2. And then it's a result object. So there are 2 person Tom's first hop neighbors. They are named Dan and Jenny, and it's a vertex object I have explained before. Also, you can use a curl to curl the endpoints that associated with this query. So I'm temporarily quit the GCQ, and I can invoke this curl commands. And the format is just your server address, 9000, and query, and the graph name, and then the query name. And then after the question mark, you can put key value parameters. So I put Tom, then it returns Tom. So I can try Jenny. Then it returns the first neighbor of Jenny. So I'm returning back to GCQ. I just type GCQ. And now I'm going to talk about a more advanced feature of GCQ. And I'm using the running example hello 2. So I'm moving the screen a little bit up. So from line 65 to line 84, and that's the body of the hello 2 query. This time, I'm going to introduce the accumulator concept of GCQ. Think about this. When you traverse a graph, you can leave some marks on any node that you encounter. And these marks can be viewed as runtime attributes of the vertices. Then when you encounter these vertices again, you can check these runtime attributes of the vertices and combine them with your new knowledge since the last time you have seen these vertices, and make some more combined runtime decisions. For example, if a person node can have some static attributes describing their age, gender, and the living states. Also, GCQ query allow people to add runtime attributes to this person. For example, the simplest one, I can use the Boolean runtime attributes to mark this vertex, whether I have seen this person node or not. In GCQ, all the runtime attributes are defined by a special built-in types. They are called accumulators. Line 67 and 68 are 2 accumulators. They got this name because they must implement accumulation operator. And the accumulation operator is just a plus equal. See the example, line 74. So all the accumulator can only accept values where the plus equals sign or just assignment equal sign. And accumulator can either be local or global. So let me elaborate on that. A local accumulator means once I declare this accumulator, it will reserve a space in every vertex in this topology. So here I use the all accumulator to design a local accumulator. So how do I indicate it's a local accumulator? I put an @ symbol prefix before the accumulator name. And this means a Boolean OR accumulator is reserved for each vertex. And its initial value is false. And means before my query starts, I never see any vertex in this topology yet. And the accumulation operator semantics for the OR accumulator means I can keep accumulating Boolean value into this state variable by OR operation. And here, another accumulator is called average age, and the type is average accumulator. It's also a built-in type. And this time I put 2 double @ symbol before the accumulator name. So it means a global accumulator. In the global memory space, I reserve a variable space for this average accumulator. And by its name, it means you can keep accumulating float point value into this accumulator, and it always returns the average value that for all the value it has seen. And in Hello 2, so I will show how to use this accumulator. As before, we start the input parameter P, and we assign that to the vertex set start. And then following this query block, I have two more query blocks. And the first query block is getting the first hop neighbor of the starting point. And the second query block getting the second hop vertex set from the input parameter P. And let's inspect the first block. And the first block is select from edge pattern, and the edge pattern is start, and go through the friendship edge type and go to person. And then it has a cum clause. And what a cum clause does is it has implicit parallel semantics in it. Basically, it means for all the edges that match the from clause, we parallel execute the statements in the cum clause for each edge. For example, for a given edge, if I want to mark the source and the target of this edge as visited, means I encounter them, this can be expressed by this accumulation statements. So target.visited equals to true, plus equals to true, and source dot visited plus equals to true. I can do this sequentially for each edge instance matching the from clause, or I can put them in the cum clause and do them parallelly since they are not interfering each other. After the first hop query block, we already marked all those vertices as visited that related to one hop of the input parameter. We also mark the input parameter as visited. Let's try to find the two hop away nodes in the second query block. So the second query block, I start from the first neighbor. So that's the compute results for the previous block. And this time I didn't specify the edge type and the target vertex type. And GSQL compiler can intelligently inference from the catalog what vertex type and edge type can fit this from edge pattern, and then fill them in implicitly. And this time I also have a where clause to filter those edge type further. So I filter out those edge who has I have seen their targets. And I also just put the alias colon E and colon target here to refer the position. Yeah. So in the second edge block, and we want to discover those two hop away vertices, and also we want to calculate the average age of the two hop neighbors. And this time I cannot use the cum clause. You see here I don't put a cum clause. Why? Because think about this. If I want to compute the average age of my two hop neighbors, there may be some situation. I have two edges that ending with the same target node. If I put them in the cum clause, then I would have calculated the average age for the second hop neighbor twice because I have two edge instances pointing to the same two hop nodes. So the cum clause is not right to calculate the average age. GSQL introduced a PostAcute to address this situation. For each vertex, so PostAcute is not a parallel anymore, it's a sequential. So who will reach the PostAcute? And those are the vertices that have three criteria. If you satisfy either one of these criteria, you will have a chance to execute the statement in the PostAcute. So the first criteria is you may have runtime attributes updated in the Accum class, then automatically you will be seen in the PostAcute. The second criteria, you're selected by the select class, then you will automatically be seen in the PostAcute class. Or you can directly reference some vertices in the PostAcute class, then of course they will be seen in the PostAcute class. All these vertices, either coming from source or target, will be sequentially executed for each statement in the PostAcute class. And here, since the target is selected, and they will be seen by the PostAcute class after the filter class by the where class, and this target age will be accumulated to the average age sequentially. Yeah, and finally, I print out the 2-hop neighbors, and I print out their average age. And let's try to see what's the average age for Tom that are 2-hop away from Tom. So on the left-hand side, okay, I didn't use any graph, so I need to enter a social graph. And then the average 2-hop age for Tom is 23, and the 2-hop neighbors is Emily, Kevin, Nancy. Okay, let's try another one. So I want to find the 2-hop neighbors for Jenny. Okay, the average age of 2-hop neighbor of Jenny is 24, and their name are Kevin and Nancy. Okay, so at this point I have finished the step-by-step guidance on GSQL 101. So I want to leverage the remaining time to run a deep link query on a billion edge graph. This is our benchmark data set, and it's public available. So let's first use some built-in REST endpoint to see the graph size. So this curl command will invoke a built-in function, and this function is stat vertex number, and I want to see the graph Twitter, and I can see there are 41 million vertices in this Twitter graph. Then how many edges in this graph? So let me see. So I use this built-in curl endpoints, REST endpoints, and I find all the edges and invoke the function stat edge number. Okay, so there's 1.47 billion edges. So this is the graph I'm trying to do deep link traversal. So I use the graph Twitter. And now I have already pre-installed a K-hop query. So this is a K-hop query from line 109 to line 129. So this is very similar to the 2-hop queries I covered in GSQL 101, but this time I make it generic. So I instead of using step-by-step 1-hop or 2-hop, this time I allow a parameter depth. Depth means how many hop away that I want to discover for a given vertex. So this time I use a while loop. So GSQL allow flow control in the query block body. And then I can say loop the depths, and I recursively find the 1-hop, 2-hop, and multi-hop away vertex set. And then I print the K-hop away starts vertex set size. So K-hop function query will return the K-hop neighbors count. And this logic should be pretty clear if you are familiar with SQL and procedure language. So I installed the K-hop already. So let's try some query. So I find a Twitter user 618593, 1-hop neighbors. Okay, there are 103,000 neighbors. Let's see how many 2-hop neighbor does he have. So 2-hop on this billion edges graph, it has 13 million. Okay, so next I'm going to increase the query timeout and to 100 seconds. And then I try 8-hop away. See how large is 8-hop away neighbors. And this is on a 1.4 billion edges on a single Linux box. And I'm starting with one Twitter account and trying to discover the number of Twitter followers that are 8 hop away. Okay, it returns 430. Now I want to stress this test to another extreme. I want to try 12 hop away. And let's kick it off. For this Twitter account, 618, 593, I want to discover how many Twitter users are 12 hop away. And it takes some time because, yeah, it's a billion scale graph. Okay, it returns. So it has, this particular Twitter user has 2 Twitter followers that are 12 hops away. Okay, I think this concludes today's our first GSQL 101 and deep link traversal demonstration. Thank you. And Victor?
Yeah, Ming Shi, thank you very much. I think we went a little beyond just GSQL 101. So if you looked at GSQL 101 before, you'll see that we got a little bit further than that. So I hope you appreciate that. Yeah, thank you, Ming Shi, for bringing up the slides again. If you could, I think we can go on to the Q&A now. So if there are any of you out there who have questions, remember they're on your Zoom control panel. There is a Q&A box. There's also a chat box. We do have a few questions. I'm going to start off with, I'm going to kind of go back to what we were doing earlier. So Ming Shi,
yeah.
Before we did querying, you were talking about loading data, and the data files were in CSV format. Mm-hmm. Can GSQL load data that's in other formats?
Yeah, we support semi-structured format as well, such as JSON. And we can also do other formats. Since if you read our documentation, we really close this loading problem. So we allow customized token UDF. So as far as your file as line by line, and we allow you plug in any token functions to parse the token however the way you want. Yeah.
Okay, thank you. And we have a question for Eileen. Hope you're still there, Eileen.
Yes.
Okay, you were describing how some graph query languages are more declarative. I think that was Cypher. And some are more procedural, like Gremlin. And GSQL, you said a goal was to be somewhat in between. So that's sort of the background. What does this mean for being able to translate or convert queries from one language to another?
Let me point out that we're actually not aiming to be in between, but rather to be both, regardless of what glasses you're looking at our queries. So our query language can be given a natural semantics in terms of pattern matching that would make it very related to Cypher. As a matter of fact, we can translate any Cypher query into GSQL with ease. Or you can take the exact same query and look at it in terms of traversal. And that's actually the perspective, to a certain extent, that you've seen taken by Ming Shi during the presentation of the demo. And there again, take a representative, a modern representative of this class of languages, such as Gremlin. We can take any Gremlin query and translate it into GSQL. In addition, you have seen Ming Shi talk about yet another perspective that you can visualize the computation under, namely the one of map-reduce style computation. He was telling you that in principle, you can think of every edge that is matched by the pattern in the from clause to execute in parallel, and for each of these edges we would write in parallel values into the accumulators. This is a very NoSQL MapReduce kind of thinking, and here again there are programmers we've seen who prefer to think in this way when they program GSQL.
Thank you, Eileen. We have a question that just came in while you were speaking. This one I think is from Ming Shi. Are we able to run some graph algorithms like community detection with GSQL?
Of course, yeah, we can do that. And actually, we are in the process of finalize the documentation to disclose a set of GSQL implementation of classic graph algorithm, which includes PageRank, community detection, centrality, and so on. Yeah.
Great, thanks. Actually, as a product manager, I could have answered that one because one of my responsibilities is to approve all that documentation. So I'm very familiar with what's going on there. We have another question. How easy is it to interface with a triple store so you can push data into TigerGraph?
Yeah, I can answer that question. Yeah, so what we have seen is a lot of people store data in the triple store and use a Sparkle to query them. And we do have help customers to load the triple store data into TigerGraph. And as I said, as far as we can dump the triple store data into line by line, and we can load them easily. And that's how we do that for our existing customer. And it's not a painful process.
Okay, and I think we have a couple more. So when we looked at the queries, we saw that the outputs were delivered with print statements. Is there something like a return statement? Do you return subgraphs, or can you return a subgraph from a query?
Okay, I can answer that. Yeah, so we do have query calling query features, and it's really one of the powerful features that we have seen customers use. And if I write a query, and instead of using the print statement to respond to a REST endpoints, we can use a return statement. And then another main query can call this subquery. And then the return statement will return some value that get assigned to some variable in the main query body. And that's how we return the expression. And in terms of subgraph, we can return a set of vertices and edges, and that's encoded in the accumulator. So we can think it as a subgraph.
Okay, thank you. And we have another, let's see, I'm reading right now because there's some follow-up questions on RDF style graphs, and maybe actually we could get maybe both Eileen and Ming Shi to comment on this. And I'm actually adding in my own commentary here. So the query languages that we've talked about so far are both oriented towards so-called property graphs. There is another family of graphs called triple stores or RDF, and maybe the dominant query language there is Sparkle. Can you say something about the compatibility between Sparkle and GSQL and the different types of graph storage? pretty broad question, but I think we kind of completely skipped over RDF, so I think maybe I'm leaving it open for you to say something about that.
So let me just take a short stab at it. Of course, the triple in an RDF store can be seen as an edge in the graph that we've been discussing so far, where the subject and the object of the triple correspond to the source and the target vertices, and the property itself corresponds to the edge type. So in that sense, these are very compatible data models, and the languages are similar in spirit. Sparkle is a pattern matching language. You will write your patterns, you will write variables, and then the result of matching the pattern will be actually a relational table that will contain one row for every instantiation of the variables in the pattern. So far, so good. Maybe this is the point to emphasize that this is where some of the differences come in, namely when you want to start aggregating the values that you found in the RDF graph. You will do this very much in SQL style in Sparkle, but also in Cypher, and as a matter of fact, also in Gremlin. So what you do is you have this conceptual table of variable bindings, and you can now group the table and you can aggregate it and so on. And this is rather different from what we do. What we do is totally compatible with that kind of computation, and we can totally simulate it using our accumulators. However, we noticed that when you want to traverse a large graph, you don't want to have to traverse it repeatedly. And think about what happens in SQL. If you have a table and you try to group by and aggregate it in two different ways. The same table, you want to group it on, let's say, attribute A, and then perform some aggregation, or you want to group it on attribute B and perform some aggregation. Even though it's the same input table, in SQL you'll have to write two queries and decide which one to run first. You cannot do this naturally at the same time in parallel. Whereas with the help of the accumulators, you can. As you traverse the data that corresponds to this single input table, you do a single traversal, a single read of the table, if you will, and you will aggregate depending on your needs in several accumulators, each of them corresponding to a different grouping key. And because of that, you will see significant improvement both in the conciseness of your program, but also in performance. But when it comes to expressive power, we can certainly take a Sparkle style query and translate it into GSQL.
Thank you. Okay, I think we have run to our full hour, so I want to thank everyone who joined us today and thank our speakers, both Dr. Ming Shi Woo and Dr. Eileen Deutsch. Do you have any concluding words, Emily? We just want to let you know that you can, again, download our developer edition or request an enterprise edition free trial. Just go to our website. We have a developer forum. We would love to have your questions and participation there. And connect with us through your favorite social media or through our website. Thank you again for joining us today. And if we didn't get to your question, we will follow up. If we couldn't answer it online, we will get back to you.